So today's topic is limiting reactant. Take a look at my little sandwich board here. We want to make some sandwiches, and each sandwich needs to have 2 pieces of bread, 3 pieces of lunch meat, and a piece of cheese. Well, if these are the items that I have at my house, how many sandwiches can we make? Well, you should notice with the bread, we can make 3 sandwiches. If each sandwich has 3 pieces of lunch meat and we have 12, 12 divided by 3 is 4. And if every sandwich has 1 slice of cheese, that's 5 sandwiches. So this makes 3, this makes 4, this makes 5. So what are we going to run out of? Okay, well, let's talk about a few things. We can obviously make 3 complete sandwiches, but after that, we ran out of bread. So now we have some extra lunch meat and some extra cheese. And some of you guys in the room are like, nah, I'm going to put that on my sandwich and make a bigger sandwich. That's what we would do at our house too. But for the purposes of today, we're going to run out of bread. So therefore, we call bread the limiting reactant. It is the beginning thing that we ran out of. So remember, reactants are on the left side. The lunch meat and cheese are our excess reactant, or what we have leftovers of. So I need to go to the store, need to get some more bread, and then I can make at least 1 more sandwich. So in your notes up at the top, it says limiting reactant, and it's got some space for you to put a definition. So when I talk about the limiting reactant, he's the guy that obviously limits the amount of product I can make. He runs out first. So take a second, maybe hit pause, write down that definition for me. The limiting reactant is the reactant that runs out first. Once I'm out of him, the reaction is going to quit. It's not going to keep going because it doesn't have enough ingredients for the reaction to proceed. The excess reactant on this slide, that is your reactant that has leftovers at the end. So I call it your leftover reactant. So the limiting gets all used up. The excess, part of it got used, but part of it is going to still be sitting in the bottom of your beaker, waiting for you to add some more so he can react. So again, if you need to hit pause, write down those definitions. I'm going to keep trucking. I promised I'd make it shorter today. So how are you going to spot a limiting reactant problem? If you kind of look down in the middle of the page where it says example 1 and you read through and it's talking about your aluminum and your hydrochloric acid, it gave you 2 pieces of given information. Anytime you see 2 givens, you know you're going to have a limiting reactant problem. So if you can find that in the little paragraph that you have, that's something maybe to underline. You must determine which reactant is limiting, and I'm about to show you how to do that. And then I always try to use that guy for all of my subsequent calculations. If I have to find another calculation, it's really, really dangerous to start your new calculation with an answer that you just got, because what if your answer's wrong? I know it never happens, especially to us ladies. But if we made a mistake, then everything after that would be messed up. So if you have an opportunity to go back and start with that given, I highly recommend it. So here's like a little diagram I thought was pretty useful. I showed my kids last year. This is the beginning of the reaction. Over here on the left side, you can see that the green dots are your limiting reactant and your red dots are your excess reactant. Now look at this word. We've never seen it before. They use the word reagent. Reagent is starting chemical. It showed up on different STAR tests, TAX tests, even CBAs. So don't freak out if you see that word. It just means which chemical or which starting reactant. So before the reaction, these 2 guys are in the same container, but they have not hooked up yet. After the reaction, you should notice I've got a lot of cute little red and green Christmas pears here. That is my new compound, or my new product. So this is A, this is B, and over here I made some Q. But what you should also notice is all of the green is matched up. Every single green atom is matched up with a red. But what I also want you to notice is that there are a lot of empty red ones that don't have a partner. And this is exactly like our sandwich scenario. All the bread matched up, but there was leftover lunch meat and cheese. And so there's leftovers inside that beaker. Most reactions look like this. Very, very few times have I ever given you chemicals in lab, you dumped them together, and you got perfect quantities at the end. Somebody got used up, the reaction stopped, there might be a little bit of acid still left in the container, there might be a little bit of zinc because the reaction didn't complete itself. So let me show you how to do one of these. Example 1 says we've got 3.2 moles of aluminum and we've got 10.1 moles of hydrochloric acid. Who is limiting? So really this is part A that I'm going to show you first. And while we do part A, something I always do is I always read part A, part B, and part C to kind of see where I'm going. You might need to notice in your notes these three hydrogens accidentally got printed on the next line. So I would go ahead out to the right of your aluminum chloride. I would add those 3 hydrogens out there because that's who we're about to talk about. How did I know we're about to talk about hydrogen? Look at part B. Part B said how much hydrogen was formed. So in a limiting reactant problem, I've got 2 reactants and I might have 1 product, or in this case, I might have 2. So when they ask you who's the limiting, they're basically saying who ran out first, aluminum or hydrochloric acid. There's no way to tell just by glancing. You're going to have to mathematically calculate this, okay? It all depends on the recipe. So just because you have 12 eggs, it doesn't mean you have plenty of eggs because I've got a recipe that calls for 6 eggs, which means I can only make that recipe twice. So in this instance, I've got to figure out who am I trying to make? Am I going to try to make aluminum chloride or am I going to try to make hydrogen? And so if you look at part B, it says how many moles of hydrogen are formed. So because it mentions hydrogen, I know that's where I'm headed. All right, so let me get a clean slate and show you what we're going to do. So because you had 2 pieces of given information, you know how I like to label things. Underneath the aluminum, I'm going to label the 3.2 moles. Underneath the hydrochloric acid, I'm going to label the 10.1 moles. So I have 2 starting amounts. They're asking me about moles of hydrogen. So I am going to have to do 2 train tracks. I know what you're thinking in your head, and it's not very nice. So I've got 3.2 moles of aluminum. That's my first chemical. We know, we slip it down here. I've got moles of aluminum. You should know the molar roadmap by now. We know that if we're going for moles of aluminum and we are trying to go over here to the other side, to this hydrogen over here, that we're going to have to do that by using the mole to mole ratio. So we know that we've got 2 moles of aluminum for every 3 moles of that hydrogen. We put that into our handy dandy calculator. I believe we get 4.8 moles of hydrogen. Now at this point we don't know anything. All we know is that with this ingredient will let us make 4.8 moles. You can say to yourself 4.8 sandwiches. I told you today a mole was kind of like an orange. And so in your head, you can make 4.8 pieces of product with this ingredient from your pantry. Now we're going to do the same thing with the 10.1 moles of hydrochloric acid. Our moles of hydrochloric acid come down. We know that we're trying to form moles of hydrogen. So in this case, your blue parts here are the same. So we make 3 moles of hydrogen for every 6 moles of hydrochloric acid that got used. So this is just a second ingredient in our pantry. So we put that into our calculator and we find out that it makes 5.05 moles of hydrogen. So if we go back to our definitions, who is the limiting reactant? It's the guy who runs out first. Well, this might be where your brain is kind of leaning. It's the 4.8. It's not quite accurate. Let me tell you what I mean by that. All right. So this 4.8 is the amount of product formed. It can only make the lesser amount, just like the sandwiches. Once I made my third sandwich, I ran out of bread. Once I make the 4.8 moles, I ran out of something. What did I run out of? So at this point, it's a little weird. We have to go back to the beginning of our train track and say, who made 4.8 moles? Which chemical formed 4.8 moles? And it was this guy, the 3.2 moles of aluminum. So I'm going to label him with an LR. The aluminum is my limiting reactant. So that is the answer to part A, not the 4.8 moles. And so now, well, what is this number? What is this 5.05 moles? This is the number that could be produced if we had more aluminum. So the hydrochloric acid had enough to make 5.05 moles. It could have made more, but we ran out of aluminum. So we call this hydrochloric acid the excess. Obviously, I abbreviate everything, LR and excess. I don't write out those words. And so I put a big old X over top of the higher number. I'm never going to be able to form 5.05 moles of hydrogen unless I go to the store and I buy some more aluminum because I already ran out of aluminum. I hope you're with me. If you're not, I'll catch you on the next example. But let's go to part B. This is just a prettier, cleaner example of everything that we just talked about, okay? This is your limiting reactant, the aluminum inside the top blue box. This is your hydrogen product that got formed. So there's your answer for part B. So part B says, how many moles of hydrogen got formed? And you're going to say, oh, the 4.8. Because the aluminum, who was the limiting, ran out, and the extra couldn't form the hydrogen because we didn't have enough. So here's the hard part, okay? If I didn't lose you there, this is the trickier, okay? Part C says, how many moles of excess are remaining after the reaction? So it wants you to look at your hydrochloric acid. How much were we given? This is part C. We were given 10.1 moles of hydrochloric. And now I've got to figure out how much excess was used during that reaction. That's going to tell me how much excess is left over. And you'll notice over here on the right, on the left, I'm going to subtract them to get how much excess is left over at the end. So it looks like this. We have already determined that our aluminum was the limiting reactant. We always start the excess step with the limiting reactant. And now, instead of comparing him to the hydrogen over here, we're kind of done with that step. We answered that question. They never mentioned aluminum chloride, so we don't use him either. We're going to look at this HCl, and we're going to turn our aluminum into HCl and say, with our 3.2 moles of aluminum, how much hydrochloric acid did we use? So we do our mole to mole ratio. It's just like toilet paper. You can only use those coefficients once. So we grab hydrochloric acid, give him a 6. We grab aluminum, we give him a 2. Sorry, that HCl is not looking too pretty right there. I'm using my finger to draw. And so at this point, we put it in our calculator, and let me show you what we get. We get 9.6 moles of HCl. Whoosh, whoosh. My other two things canceled out there. And so this is how much excess got used up. So if the reaction had gone perfectly and I had wasted no ingredients, I would have used exactly 3.2 moles of aluminum and 9.6 moles of HCl. But that's not what happened. Instead, I had 10.1 moles of HCl, and I'm going to subtract the 9.6 that I used. And that's going to get me the 0.5 moles of HCl that's left over. So now I believe we've answered part C. That's the gist of it. And now I started off babyish. I just did moles to moles because I'm more concerned with you understanding the process and all of the terminology rather than can you do a really long train track. I know you can because there's one on tonight's homework. All right, so let's kick it up one notch. Okay, no more basics. Here we go. Example 2 says we've got 0.8 grams of nitrogen reacting with 2.0 grams of hydrogen. Who's the limiting? Who's the excess? So we read ahead in part B, and if there's a part B, they probably are asking about NH3, which is ammonia, because that's the only product over there. So we know we're going to set up 2 train tracks. Here we go. We've got our 0.8 grams of nitrogen and our 2.0 grams of hydrogen. I don't know why I do these simultaneously, but I do. So here is my Hofrinkel nitrogen. 28.014 grams is 1 mole, because that's about the only thing I know to do with grams. Then I can do it for hydrogen at the same time. 2.016 grams of hydrogen. If you're not a nerd already, I'm going to make you one. You probably are starting to memorize molar masses of compounds and Hofrinkels. Big nerds. Oh, just kidding. That's a hydrogen. And so we're going to keep on trucking. And we know that we're going from this nitrogen to ammonia and from this hydrogen to ammonia, because we're comparing our products. And so down here, we're going to put our moles of nitrogen turning into our moles of ammonia. And down at the bottom, we are comparing moles of hydrogen to moles of ammonia. So we're coming from 2 different places, but we're ending up at the same spot so we can compare. You should notice, stoichiometry experts, here's our mole-to-mole ratio. And so we're going to go ahead and plug that in. We get that from those coefficients that we can only use once, 2. And nitrogen is an imaginary 1. Same thing on bottom, 2. But this time hydrogen is a 3. So now we've got moles, but if you look ahead, they actually asked for grams. So we got to keep on going, but let me show you the cool part. Down here at the bottom, we are going to say 1 mole of ammonia is equal to 17.0031 grams. I don't have room to put NH3 on there, sorry. And at the bottom, we get to repeat that step, so you get to use it twice. So even though we're doing 2 train tracks, it's a little validating to say, hey, I get to use that number over again. So that's kind of okay. We get some crazy contrasting answers on this one, so check this out. When we crank out our nitrogen one and we put it in our calculator, it comes out to be 0.97 grams of ammonia. If we wanted to get crazy on sig figs, we're talking 1 gram of ammonia. And when we come down to this second one for hydrogen and put in our calculator, it comes out to 11 grams of ammonia. So what a huge difference. So with the ingredients in my pantry, my nitrogen will let me make about 1 gram. but my hydrogen will let me make about 11 grams. So you tell me, who's going to run out first? All right, don't forget, it's not the guys on the right, it's the guy on the left. So our nitrogen ends up being our limiting reactant, so I always label that very clearly. And our hydrogen is going to end up being our excess or our extra. I always, on the other side, I'm going to cross out that 11 grams because I know I don't have enough nitrogen to form that much ammonia, so I don't want to accidentally use that number for any reason. So we've answered part A, which is always, who's the limiting reagent? Okay, and even though they don't ask us specifically sometimes who's the excess, I go ahead and label. So our limiting reagent is our nitrogen, our excess is our hydrogen, and then this is what, do you remember? This is your product formed from the limiting reagent. And so it's not a bad idea to label that as the product formed by the LR, by the limiting reagent. Sorry, my handwriting's pitiful. So let's keep booking it. So here's the nice pretty copy of everything that I just did. All nice and cutesy. We said that the nitrogen was the limiting reactant and the hydrogen was the excess. Now you know what's coming next, your favorite part. How much excess remains? So this time, since they gave us grams, we're going to give them grams back. We always try to keep it consistent. If they give us moles, we give them moles back. If they give us grams, we're going to give them grams back. If you remember from the first example, we're going to take our limiting reactant, and instead of jumping over top of that arrow, going to the other side, for the excess step, we're just going to go right next door and say how many grams of hydrogen got used. So it looks like this. 0.8 grams of nitrogen. You get to reuse all of your numbers from earlier. Kind of nice. 28.014 grams of nitrogen is 1 mole of nitrogen. We're going to do our mole to mole ratio next. And we are comparing nitrogen to hydrogen. So when you look at their coefficients, there's an imaginary 1 in front of that nitrogen, and there's a coefficient of 3 in front of hydrogen. But we got to keep going because we got to get grams. Down here, we're going to have moles of hydrogen, and we're going to change it into grams. So if you go back up into your previous train tracks, you'll see all that information. 1 mole is 2.016 grams. And after some magical calculating, we end up figuring out that there is 0.17, or if we did sig figs, 0.2 grams of hydrogen got used. So many questions today on the quiz. Does this 0 count? And y'all were looking at these leading zeros. The answer is heck no, they never count. I need to write them as placeholders, but they don't count. Well, what if it's 0.061? Does this 0 count? It's after the decimal. Nope, it's still leading. Neither one of them count, but we write them to hold their place. But other than that, they don't mean squat. So we figured out how much we used. Now we need to figure out how much is left over. And that's the question that they always ask. So we start with how much excess you started with. Do you remember? If you look up at the top, it said we started with 2.0 grams of that hydrogen up there. So we're going to say we started with 2.0, and now we used 0.2, and when we subtract, we find out that 1.8 grams of hydrogen remains. Or you can write as leftover, whatever makes you happy. All right, that's how to do limiting reactants. I would say if you think you get those two examples and you can start on page 114, you can quit. I'm probably going to keep going and do one more example. For those of you who aren't quite sure, it's up to you whether you watch it or not, okay? You can always come back and watch the end of the video, but I promised some people some jokes, so stand by. This is an oldie but goodie, but I do happen to love it. Girls, don't ever do this. I don't know if they're worth it. I got another one. Totally think this should be the science department shirt. I don't think Mr. Simmons would go for it, but it's funny. All right, good night, stay warm, and I know you're going to go do your little snow dance in the front yard. It's already starting to form, so be safe, be careful, bundle up. All right, let's hit it. We've got 110 grams of calcium hydroxide. It's reacting with 96.6 grams of hydrochloric acid. How many grams of each product will form? You're not going to like this. And how many grams of excess remains? So if you ever run into one of these, it looks like, oh my God, I got to do 2 train tracks to get over here, and I got to do 2 more to get over here. Not necessarily true. Let me save you at least 1 track. So yes, you're going to have to do at least 3 tracks just to answer part A. And it's kind of sucky, but you know, we'll get over it. And if this eraser worked any better, I could actually get on with life here. All right, I'm such a perfectionist. It's dirty. Okay, so I am going to start with my 110 grams of calcium hydroxide. And I'm going to train track that bad boy to moles. I'm going to come back and fill in all those numbers later. Doesn't matter which product we pick first. Just for giggles, I'll pick this first one, calcium chloride. So that's where we're headed. So I'm going to go from my 1 mole of calcium hydroxide to my 1 mole of calcium chloride and 1 mole of calcium chloride is going to go to grams of calcium chloride. Now for molar masses. Calcium hydroxide over here is 74.092. Calcium chloride is 110.984. And we're going to calculate. My calculations tell me I am getting, let's see, 4 sig figs, 164.8 grams of calcium chloride. So we don't know yet if that's how much got produced because we have to run another train track. Here we go. I'm going to do it in another color here. We've got 96.6 grams of hydrochloric acid. We're going to take our grams of hydrochloric acid, change it into moles of hydrochloric acid. Once we're in moles, now we can jump over here to calcium chloride. So we're going to go to moles of calcium chloride, do our diagonal, moles of HCl. You should notice off the bat, there is your mole to mole ratio. It in fact is a 1:2 ratio. And we keep going and saying that 1 mole of calcium chloride hasn't changed since a minute ago. It is still 110.984 grams. I love that we get to use those molar masses at least twice. Go back and put in your HCl, and it's 36.461. And we calculate, and we get 147 grams of calcium chloride. So if we take a look at this, what are we trying to figure out? Who's the limiting reactant? So I look at my two numbers, 164, 147. The 164 is the big one, so we exit out. So this is the product formed. So we answered one of the questions up at the very, very top. It said, how many grams of each product will form? So I can automatically come up here and say, oh, this answer is 147 grams. Now, technically, they didn't ask who the limiting reactant was. That makes me nervous. So I am going to go back to the front of here, and I'm going to label him as my LR. And the one that I X'd out, conveniently, is my excess. So whichever answer you X out came from the excess. Whichever one you put a box around and keep came from your limiting reactant. So we still have to come up with water. Here's the beautiful part. Since we already know that the HCl is the limiting reactant, rather than doing both of these to make water, I can just start with this guy and make water because he is the limiting reactant. Because why do two train tracks if I'm just going to X out one of them again? I know that this is going to get me the right answer. Figured out how to scoot that up a little, get some more room. So we are going to take that same 96.6 grams of HCl and literally copy down everything again. Until we get to that mole ratio. So now, remember, we're changing to water. So we need to use the 2 moles of H2O. And we need to use water's molar mass, which you should know by now, 18.015. It's the same every time. And I get 47.5 grams of water. So up at the very top, under my water in this blank that you can barely see, we can put our 47.5 grams of water. So now we know who's limiting, we know who's excess, we know how many grams of each product form. So at this point, we have to figure out how many grams of excess are left over. So let's recap. Who is the excess after all of this? This 110 grams of calcium hydroxide was your excess, this guy. So if we used up all 96 of these grams, I want to know how much of that 110 is still left. I'm going to go to a new slide, give myself some more space. So since this guy was my limiting reactant, that's who I'm going to start with, 96.6 grams of HCl. I'm going to go from my grams of HCl to moles. I'm going to go to my mole to mole ratio, which is a 2-to-1 ratio because I'm going from limiting to excess. It's 2 moles of hydrochloric acid for every 1 mole of calcium hydroxide. And 1 mole of calcium hydroxide is my G units of calcium hydroxide. So I'm going to go back up into those other 2 train tracks and I'm going to find the molar masses because I don't want to recalculate. Hydrochloric acid is, whoa, need a pen, 36.461. Calcium hydroxide is 74.092. We put all this mess into our calculator. Our final answer is 98.1 grams of calcium hydroxide got used. But that wasn't what they asked us for. They said how much excess remains. So if you remember, we have to go back up here and say how much excess did we start with. Since he's our excess, we started with 110 grams. We used up 98.1. And that leaves us with an 11.9 grams of calcium hydroxide remains. And that is the story. Make sure you're at school if we have school on Thursday or Friday, whatever day we go back. And we are going to do some food. I bought it. It's in the car. It's ready to go. Might be a little frozen, but it's good. Have a great and wonderful evening. We will see you soon.